Ever wondered how to design effective test cases for your code? One way is by using the Cyclomatic complexity method. Cyclomatic complexity is a software metric that measures the complexity of a program's control flow. Think of it as a roadmap of your code, where each route represents a different path through your program. This metric provides valuable insights into the number of independent paths within your code, which can help you identify areas that might need more rigorous testing. The more complex your code, the more paths it will have, and the more test cases you will need to ensure it's functioning correctly. So how do we calculate cyclomatic complexity? Well, we use a formula, Vg equals E minus n plus 2 times p. In this equation, E represents the number of edges in the control flow graph, n is the number of nodes, and p is the number of connected components. For a single program, p is typically 1. Once you've calculated the cyclomatic complexity, you can start to identify the independent paths through your code. Each of these paths represents a unique sequence of control flow decisions and branches. By designing test cases that cover each path, you ensure comprehensive testing of your code. Don't forget to consider both positive and negative test cases. These will validate different conditions and outcomes, ensuring your code can handle a variety of scenarios. But how do you choose the right data for these test cases? Well, you'll want to consider boundary values, corner cases, and edge cases. These help to ensure your testing coverage is thorough and that your code can handle a range of inputs. Finally, execute your test cases and record the results. Review these results to identify any discrepancies or failures, and use this information to iterate and improve your test case design. So, by understanding the cyclomatic complexity of your code, you can identify the number of test cases needed for comprehensive testing. By focusing on these areas, you ensure your code is robust, reliable, and ready for any scenario. Once we have calculated the cyclomatic complexity, the next step is to identify independent paths in our code. This process involves analyzing the control flow graph of our code. But what exactly is a control flow graph? It's a graphical representation of all the paths that might be traversed through a program during its execution. It's made up of nodes and edges, where nodes represent blocks of code, and edges represent the flow control between these blocks. Independent paths are the unique sequences of control flow decisions and branches in the code. Each path is a series of nodes linked by edges, which starts from the entry node and ends at the exit node. The key here is to focus on independent paths, which means each path should introduce at least one new edge that was not covered by the other paths. To identify these paths, we start from the entry node and trace each possible route to the exit node, marking the edges as we traverse them. The first path is usually the one with no decision nodes, meaning it doesn't branch off. For subsequent paths, we trace routes that include untraversed edges, ensuring we cover all decision points, loops, and branches in the code. Do remember, each of these paths represents a unique scenario or behavior of the program, which needs to be validated through testing. For instance, in a program with conditional statements, each condition and the code block executed as a result would constitute a separate path. As an example, consider a simple if-else statement. It has two independent paths, one where the if condition is true and the other where the if condition is false, leading to the else block. Both these paths need to be tested to ensure the program behaves as expected under different conditions. By identifying these paths, we can ensure that our test cases cover all possible scenarios. This, in turn, leads to thorough testing coverage, providing us with the confidence that our code is functioning as it should. So, let's keep moving forward on this journey of designing effective test cases using cyclomatic complexity. Now that we have identified the independent paths, it's time to design our test cases. Creating effective test cases is a crucial step in the process. Each test case should cover a distinct path through the code. This ensures that all decision points, loops, and branches in the code are put through their paces. Let's start by creating a test case for each identified path. This might sound like a daunting task, but it's essential for comprehensive testing coverage. The aim is to validate different conditions and outcomes, so don't shy away from crafting both positive and negative test cases. For instance, if you're testing a function that calculates the grade of a student based on their score, you would create a test case for a score that is equal to or greater than 90. This will cover the path where the function returns an A. Similarly, you'd design another test case for a score that is less than 90, to cover the path where the function does not return an A. Next, we need to select representative test data. This is the input data and test data values that will be used in each test case. Remember, the goal is to exercise different code paths and conditions. So consider boundary values, corner cases, and edge cases. This ensures that your testing coverage is as thorough as possible. Once you've designed your test cases and selected your test data, it's time to execute the test cases against the code under test. As you do this, record the test results and verify that the code behaves as expected for each test case. At this point, you might be thinking, "Great, I've executed my test cases, I'm done." But hold on, there's one more important step. You need to review the test results and identify any discrepancies, failures, or defects that the testing may have uncovered. Analyze the effectiveness of your test cases. Are they covering all the different code paths and conditions? If not, it's time to iterate on the test case design process and address any gaps or deficiencies. Remember, the goal is to ensure comprehensive testing coverage. By using the cyclomatic complexity technique, you can design test cases that provide a thorough examination of your code, helping you build software that is robust and reliable. With our test cases designed, we now need to select our test data and execute the test cases. Selecting test data is as crucial as designing the test cases themselves. We have to pick suitable input data and test data values for each test case. The aim is to exercise different code paths and conditions. We need to consider boundary values, corner cases, and edge cases. Boundary values are those values at the extreme ends of an input domain. Corner cases are scenarios that occur outside of normal operating parameters, specifically when multiple environmental variables or conditions are simultaneously at extreme levels. Edge cases, on the other hand, are scenarios that occur at the extreme operating parameters. Once we have our test data selected, it's time to execute the test cases. We run the designed test cases against the code under test. This is where we see the fruits of our labor. As we execute these test cases, we record the test results. This is critical because it allows us to verify that the code behaves as expected for each test case. If it does, great. If it doesn't, then we've identified a potential issue that needs to be addressed. This process of executing test cases and recording their results helps us understand how the software behaves under different conditions. It's like taking the software for a test drive under various weather conditions and road types to see how it performs. It's not just about finding defects or errors. It's about understanding the software, its strengths, its weaknesses, and how it behaves under different scenarios. Remember, the goal is not just to find bugs. It's to understand the system we're testing. That's why it's crucial to carefully select our test data and meticulously record our test results. Only then can we truly verify that the code behaves as expected for each test case. Through this process, we can verify that the code behaves as expected for each test case. After executing our test cases, we must review the results and iterate on our test case design process. Now, let's dive into the significance of reviewing and iterating. Reviewing is a crucial step in the process, as it allows us to evaluate the effectiveness of our test cases and identify any discrepancies, failures, or defects that may have surfaced during testing. Discrepancies may include unexpected output or erratic behavior of the code, which could indicate a potential issue. Failures, on the other hand, are instances where the code does not meet the expected outcome defined in our test cases. Defects are more severe and may involve code crashes or system instability. In identifying these, we're not just looking for what went wrong. We're also discovering areas of our code that may need more attention or where our test cases may have fallen short. This process of identification can highlight whether our test cases effectively cover all the potential paths and decisions within the code. Once we've reviewed the results and identified any issues, the next step is to iterate on our test case design process. This means revisiting our test cases and refining them based on the findings from our review. Iteration can involve creating new test cases to cover previously untested paths, or adjusting existing ones to better account for different conditions. It's important to remember that this is an ongoing process. As we continue to iterate and refine our test cases, we're continually enhancing the coverage of our code and improving the overall quality of our software. This iterative approach is what makes cyclomatic complexity such a valuable tool in test case design. It guides us in identifying the most critical areas of our code and helps us prioritize our testing efforts. And there you have it. That's how you design test cases using cyclomatic complexity. This method ensures thorough testing coverage and effective validation of your code.